Hello, on section 2.4, day 2, we're going to calculate the instantaneous rate of change today in a lot of different applications. And this is the very last section of chapter 2. First example, free fall. The object is dropped from the top of a 500-meter tower. Its height above the ground after t seconds is 500 minus 49t squared. How fast is it falling after it's dropped? Okay, we're going to take the limit as h goes to 0 to find that rate of change. And we're going to take the function at 4 plus h and subtract the function at 4. And then we're going to divide that by h, or 4 plus h minus 4, which is just h. All right, let's calculate that. And remember, we're going to have to do just a little bit of fancy algebra. First, we take our function and plug in the 4 plus h value. Don't forget to square it. And then we're going to subtract the function at 4. So that's equal to 500 minus 4.9 times 4 squared. All right, whatever that quantity is. Okay, so now we have 500. Oh, we're going to divide that by h. Don't do that. Divide that by h. 500 minus 4.9. We're going to have 16 plus 8 h's plus h squared minus, I'm just going to leave this number like it is, 500 minus 4.9, 16. These are acting not squared anymore because I just squared it. Divide that by h. Okay, let's simplify that just a little more. 500 minus, now don't forget to distribute this, negative 4.9 through everything. So negative 4.9 times 16 plus, or I'm sorry, it'll be minus. Well, minus 4.9 times 8h minus 4.9 times h squared minus this whole thing, 500 minus 4.9 times 16. All right, now if you take a look at this, we have 500 minus 500. We have this negative 4.9 times 16 minus negative 4.9 times 16. All right, so what do we have left? Minus 4.9 times 8 h's minus 4.9 h squared all over h. Okay, what is negative 4.9 times h? I think that's negative 39.2. We have h over h, which cancels out, and we can go ahead and do that, and then this one just becomes a 1. So we have minus 4.9 with 1h. We take the limit of this. I didn't write all these limits. H goes to 0. Of this whole thing. If we do that, the second term goes to 0, and we end up with negative 39.2. And it's meters per second. Yes, meters per second. And that will be our instantaneous rate of change at t equals 4. All right, a little bit of calculus, a lot of algebra. What's the rate of change of the area of a circle with respect to the radius? Okay, so the area of a circle equals pi r squared. So what we're going to do is take this equation and at r equals 3, we want to find the rate of change at r equals 3. So we're going to compare that with r equals 3 plus h and find the rate of change between those two points. we have the limit. This slope or rate of change is going to be, the limit as h goes to 0 of pi times 3 plus h squared minus pi times 3 squared all over h. Let's simplify this a little bit. We're going to do lots of FOILing here for a few days. 3h plus 3h is 6h. Okay, so let's simplify this again. And don't forget, 3 plus h squared, that 3 plus h squared equals 3 plus h times 3 plus h. Sometimes people forget that, even calculus students. So please keep that in mind because it happens in this class a lot. So now I'm going to distribute this pi and do all of this algebra. 9 pi plus 6 pi h's plus pi times h squared minus 9 pi's all over h. We're going to take the limit of this as h goes to 0. Okay, 9 pi's minus 9 pi's cancel out. We're left with 6 pi h plus pi h squared on the top. So the instantaneous rate of change of this circle when the radius equals 3 is 6 pi h over h is just 6 pi's. And if I distribute it over here, I get pi h. Now we're going to send h to 0, and we're going to end up with 6 pi. Our rate of change is going to be 6 pi inches per, I don't think it told us what. Yeah, 6 per time. Whatever the time unit is, that is going to be our instantaneous rate of change at r equals 3. This time, oh, whoops, times radius. Actually, it's not inches per time, it's per radius, isn't it? Okay, and that is the instantaneous rate of change. Actually, you know what it is? It's inches squared per inch, I believe, because it's the change in inches over the change in inch. I'm going to have to check that unit. That's a good question. Should have been a geometry teacher, right? Find an equation for each tangent to the curve that has a slope of 2. So, oh, this is fun, because now we're going to do some tricky stuff. We're going to do the same equation, but now we already know what the instantaneous rate of change is. This equals 2. So we're going to set up 2 equals the limit as h goes to 0 of this equation. The difference here is we don't know what x is. So we're going to use x and x plus h to try to figure out exactly what x is. So we have 9 minus x plus h squared. That's our first function, minus 9 minus x squared. And all of that is over h. So let's simplify that. 9 minus x squared plus 2xh's. Oops, this is going to be a minus again. Don't forget to do that minus. It will come back to bite you if you don't. Okay, x squared minus, because remember this minus is distributed all through here. Minus x squared minus 2xh minus h squared minus 9 minus x squared. All right, we have 9 minus x, well, it's all over h. 9 minus x squared here and 9 minus x squared here. That leaves us with minus 2xh over h minus h squared over h. This is the limit as h goes to 0, and that is equal to 2, because our instantaneous rate of change is 2. We're getting closer. We have minus 2x's minus an h. And we need to take that limit as h goes to 0. All right, so our h goes to 0, and it leaves us with minus 2x's. Minus 2x's equals 2. If we divide both sides by a negative 2, what do we get? We get x equals negative 1. All right, that's our x value. Is that all we need? Find an equation for the tangent to the curve that has a slope of 2. So we have a slope, we need a point. All right, and so far we know that x equals negative 1. We need to calculate a y, but we already have m is 2 because that was given to us. So we're going to take y as 9 minus x squared. 9 minus negative 1 squared equals 8. All right, so our y value is 8, our x value, we can write the equation of the line. I know we can, because we are good like that. So, real quick, y minus 8 equals 2 times x minus a negative 1, or x plus 1. That is equation tangent to the curve. The next problem is, this one's a little tricky, but not really. What point does a function have a horizontal tangent? Well, a horizontal tangent means that the slope equals 0. Therefore, we put 0 into this equation. Don't forget our limits. So 0 is our m, and we're trying to find x. What point? Actually, we probably need an x and a y, but once we find an x, we got a y, because we have an equation. All right, so we're going to take the limit as h goes to 0 of 3 minus 4 times, again, we need to put in x plus h minus x plus h squared minus the whole function here, 3 minus 4x minus x squared. All right, and you might notice that the second part of this equation always seems to cancel out. And that will hold true this time too. 3 minus 4x minus 4h minus, we have to expand that, minus x squared minus 2xh minus h squared minus this whole equation again. This is just a whole lot of algebra going on. Okay, 3 minus 4x minus x squared. 3 minus 4x minus x squared gets rid of that. Okay, let's see what else we have here. Minus 4h's minus 2xh's minus h squared. That's what's left on the top. Divide that all by an h to see what we have left. All right, 0 equals negative 4 minus 2x's. Because these h's are canceling out with each of those terms. This one is, we have an h left, right? Minus h. And don't forget, we need to take the limit as h goes to 0 of this whole thing. All right, so h goes to 0. We have negative 4 minus 2x, and that equals our instantaneous rate of change, 0. Here we can calculate x by adding 4, dividing by a negative 2, and we get x equals negative 2. We can also plug the x into the y value, which is 3 minus 4x minus x squared. If you plug a negative 2 in here, plus 8 minus 4. So y equals 11 minus 4, or 7. X is negative 2, y is 7. So this is the point. Point where the slope equals 0 of the tangent line. It's called a horizontal tangent. And that is the end of our tape today. Arrivederci!